Discover Geography, Lesson 3-1, Plate Tectonics. Plate tectonics helps us to explain the broad-scale patterns of our Earth's surface. Why is there ocean here and dry land there? Why are there mountains in certain places? And why are there islands in other places? Plate tectonics helps us to explain the movements of our continental masses over the course of long periods of the Earth's history. This is a process known as continental drift. What you see here is a reconstruction of what the Earth looked like 650 million years ago. The little black pointer shows the location of what is now Slippery Rock, Pennsylvania. You can see that 650 million years ago, Slippery Rock was underneath an ice cap near the South Pole. If we follow the motions of the continents from then towards the present, we can see North America breaking away, moving up towards the equator, eventually joining with all of the other continents to form a supercontinent known as Pangaea, and you can see Slippery Rock there near the center of this continent of Pangaea. And then Pangaea begins to break up about 152 million years ago with the formation of the Atlantic Ocean as our continents move towards their current positions. Continental drift will continue on into the future. And so based on our understanding of the forces that are causing this movement, we can project possible future scenarios. So here's one potential future situation where the continents have reconvened into a new supercontinent. And you can see there where Slippery Rock would end up right next to Africa 250 million years into the future. To understand why continents would move like this, we have to look at the interior structure of the Earth. What's going on underneath our feet? We can divide the interior of the Earth into a series of layers. The outermost portion of the Earth, which may be anywhere up to 100 kilometers thick, is known as the crust. And the crust is a layer of solid, brittle rock. And the crust comes in two different varieties, and you can see those at the top of the pie slice diagram there. You can see some much thicker crust underneath the continents and thinner crust underneath the oceans. And this is going to become important to our plate tectonics, that we have thicker, more buoyant crust underneath our continents and thinner, more dense crust underneath our oceans. The next layer down is the mantle. And the mantle can be subdivided into several sublayers. The uppermost part of the mantle is, like the crust, also made of solid rock. And so the upper mantle and the crust together are sometimes referred to as the lithosphere. So this is this outer shell of hard rock on the outside of our Earth. The middle part of the mantle is known as the asthenosphere. The asthenosphere is made of molten rock. The heat and pressure at that level inside the Earth are high enough that the rock becomes a sort of tar-like consistency. It's not quite liquid, but it's molten enough that it can flow and move. And so our lithosphere is essentially floating on top of this molten asthenosphere layer. And as we go down past the asthenosphere, we have the lower mantle, which is solid rock again. And then we have the core. And the outer core is liquid, and then the inner core is a solid mass of mostly iron and nickel. And it's this inner core spinning there inside the liquid outer core that generates our planet's magnetic field. And we've already talked about how that magnetic field is what makes our compasses point to magnetic north, which is slightly off from true north. This outer shell that's made up by the lithosphere is not one solid piece. It's broken up into chunks that we refer to as tectonic plates. And so the movement of continents in continental drift is really the movement of these tectonic plates as they rearrange themselves on the outside of the Earth. And they're driven by movement within the asthenosphere. As that molten rock within the asthenosphere flows in different directions, it drags these chunks of lithosphere around with it. And you can see on this map the current directions of motion of some of our major tectonic plates. So the North American plate, for example, that encompasses all of the continental United States, as well as Canada, Greenland, and a bit of Siberia, is moving in a generally westward direction, as is the South American plate, whereas the Eurasian plate and African plates are moving in an eastward direction, and the other plates you can see from the arrows all have their own directions of movement. This movement is extremely slow. This could be on the order of millimeters per year. So there hasn't been a substantial rearrangement of the locations of our land masses within the scope of human history. But within the scope of millions of years of movement of the tectonic plates, they've generated the landscapes that we see today. When we look at the motion of tectonic plates, most of the real action, most of the things that are really going to shape what the landscape is like on the surface of the Earth are happening at the boundaries between the plates. So we want to look at the different types of plate boundaries that we might see. The first type to talk about is a divergent plate boundary. Divergent means moving away. So this is what happens when we have two plates that are moving in opposite directions from each other. And a divergent plate boundary will often start as a rift valley. So we may have a continental mass that begins to split into two pieces. So this big kind of crack opens up. And we have a prominent one of those on the world today, which is the African Rift Valley that runs down the eastern side of Africa. The continent of Africa is currently in the process of splitting in two. And that will be a process that takes millions of years. It's not something that we'll see in our lifetimes, that we may not see within the scope of human civilization. But it's something that's occurring on a geological timescale. As those two pieces start to move away from each other, we get a little gap. Molten rock is going to come up from the asthenosphere and harden and create new lithosphere to fill in that gap. And the new crust that's formed at the top of that lithosphere is always going to be oceanic crust. We're not going to see new continental material produced as the two sides move apart. Instead, we're going to see oceanic material. So we're going to get a new ocean basin forming. And so the Red Sea between Africa and the Arabian Peninsula is the northern end of that rift valley. It's split apart far enough that it's now filled with water. And if those plates continue to diverge, we get an entire ocean forming in between them. And right down the center of that ocean is going to be a mid-ocean ridge. This is an underwater mountain chain that's formed at that point where these two plates are moving away from each other, and so new oceanic crust and new lithosphere are being formed to fill in that gap where those two plates are moving away from each other. And there you see a picture of a mid-ocean ridge. You can see some of the hot steam coming up out of where the asthenosphere is forming new lithosphere on the surface. We can also have a convergent plate boundary, where two plates are moving towards each other. And what happens at a convergent plate boundary is going to depend on what kind of crust is on either side of that boundary. So we can start with a continent-to-continent convergent plate boundary. Two continents ramming into each other. And what that will form is a huge mountain range. These two continents crash into each other and it piles up huge mountains. The highest mountains in the world today, the Himalayas between China and India, are being formed by a convergent continent-to-continent plate boundary, as India is basically ramming into the rest of Asia. The Appalachian Mountains in the eastern United States were formed in this way as well. When Africa collided with North America in the formation of that supercontinent of Pangaea, it created an enormous range of mountains, possibly the highest mountains that we've ever had in the world. In this case, those mountains stopped being pushed up when the direction of plate movement reversed and North America and Africa split apart. And so they've had millions of years to erode down. So that's why the Appalachians aren't as high as the Himalayas. If you have a continent-to-ocean convergent boundary, you get something a little different going on. So we said that the continental crust is thick and buoyant, whereas the oceanic crust is thinner and denser. So when a continent and an ocean plate are pushing against each other, the continental plate is going to tend to ride up on top of the ocean plate. The ocean plate's going to get pushed down underneath the continental plate. This is a process known as subduction. So subduction is when a piece of oceanic crust is being pushed down underneath another plate. When this happens, the first thing we get is an oceanic trench. So there's kind of a V-shaped valley where the one plate is getting pushed underneath the other. And this will be right off the coast of the continent. The second thing that happens is as this plate gets pushed down into the asthenosphere, it begins to melt because temperatures in the asthenosphere are so high. The molten rock then begins to flow back up towards the surface, and it will come out in the form of a series of volcanoes. So we get a volcanic mountain range forming on the continent. So we can see that, for example, in the Andes Mountains on the west coast of South America and in the various mountain ranges on the west coast of North America, the Rocky Mountains, the Sierra Nevada, the Coast Ranges. So here you see Mount St. Helens, a famous volcano in the state of Washington. So we've got the Pacific plate being subducted underneath the North American plate, and that material is coming back up to the surface in the form of volcanoes. Here you see an ocean trench of the type that's located right off the west coasts of both of the American continents. Finally, you might have ocean-to-ocean convergent boundary, two ocean plates ramming into each other. In this case, we also get subduction. One of the ocean plates will end up subducted under the other, and so we'll get an oceanic trench, just like we got with the ocean-to-continent convergence, and we'll get the formation of a volcanic mountain range, just like we did with the ocean-to-continent convergence. The main difference here is that because that volcanic mountain range is now located on oceanic crust rather than continental crust, instead of a volcanic mountain range on land, we get a series of volcanic islands. So anywhere you see an arc-shaped archipelago, a series of islands that form an arc shape, those are being formed by ocean-to-ocean convergent plate boundary, and those islands will generally be of volcanic origin. So the Aleutian Islands off of the coast of Alaska are an island arc formed by ocean-to-ocean convergent plate boundary, as are the islands of the Caribbean. So here you see a picture of the island of Montserrat, which has a very active volcano. It's being formed as the South American plate and the Caribbean plate, which both have oceanic material at their edges, are converging. So since our oceanic crust is being created at divergent plate boundaries and being destroyed through subduction at ocean-to-continent and ocean-to-ocean convergent plate boundaries, if we look at the age of our ocean floor, the age of the lithosphere at the bottoms of our oceans, we can actually see this process happening. We can see the newest oceanic crust located along those mid-ocean ridges where divergent plate motion is happening. And the oldest lithosphere is up against some of those ocean trenches where it's being subducted underneath a continent. So the floor of our oceans is essentially recycled every few 100 million years. You can see some of the oldest ocean lithosphere is less than 300 million years old, when our whole planet is billions of years old. The continents, on the other hand, are fairly stable. We don't get creation of new continental crust on a large scale or destruction of continental crust on a large scale. So we have areas of some of our continents, areas in northern Canada or in Western Australia, for example, that are essentially as old as the Earth, that go back to the earliest time that the surface of the Earth cooled into hardened rock. So essentially our continents are moving around, and the ocean is getting destroyed and created in between them to fill in the gaps.